Hi, everybody, and welcome back. Today, I thought we would continue on and finish up with the the first and the second derivatives, and specifically talking about position, velocity, and acceleration. So, yesterday we had learned, let me make sure my pen is on. All right. If you have a position function, usually given by s of t, all right, that's the most common one, it has a derivative. And rather than calling it s prime of t, we just call it v of t. Because as it turns out, the derivative of position is velocity, right? How fast an object is moving. And then the derivative of velocity, we tend not to call s prime, all right? We don't call it v prime, even though that's what it is. We end up calling it a of t. Position is measured in some unit of distance. It can be as small as inches. It can be as long as miles or kilometers. Velocity, right? So my position is given in like inches. My velocity is given in like inches per second, inches per minute, miles per hour, and then my acceleration would be in inches per second squared, miles per hour squared. Positive velocity means you're moving forward or up. You're going in a positive direction. Negative velocity means that you're moving either backwards or down in a negative direction. A positive acceleration means you want to move in a forward direction or a positive direction. And a negative acceleration means you want to move in a negative direction. Okay, so I want you to take a minute here, copy down the first part of this problem. Okay, we are told that the t is measured in minutes, and we're told s of t is measured in feet. So the directions here are find the velocity and the acceleration functions. We know the velocity is just the first derivative, 3t squared minus 12t plus 9. This problem is set up to use your power rule. And the acceleration is the derivative of velocity, 6t minus 12. Now, many of you should be able to look back at problems that you've done, like in a physics class, all right, with position, velocity, acceleration, and start to see where a lot of these formulas have come from. Okay, part B, find the position, velocity, and acceleration when t is equal to 4. So we're just going to take each of these functions and plug in t is equal to 4. See, for s of 4, you actually get 4 back. And the units here, I believe, were in feet. For v of 4, you should get 9 back. And the units here would be feet per, it wasn't second, it was minutes. Right, remember, this is an example of a slope, and that's exactly what that rate tells you. Feet is the change in y, minutes is the change of x. And for acceleration, I plugged in 4 and I got 12 back, and this would be feet per minute squared. Now, once you have a position function, right, and you can find these other two functions, you can use them to solve a lot of problems. What'll end up happening in a calculus class is you're actually going to start with the acceleration function and some other information, and then you're going to do the antiderivative and get velocity and antiderivative to get position. So in a calculus class, you're given very limited information, but your job is to come up with those three equations. All right. And as you'll see, when you get to that point, it's actually not that difficult. But then you want to start using those three equations. So for right now, we're going forward, just finding the derivative, and then we want to use it. For part C, when is the object at rest? So you got to ask yourself, what does that mean if the object is at rest? And the object is at rest here when my velocity is equal to 0. That's what I want to know. When is my velocity? Now the formula for velocity was 3t squared minus 12t plus 9. I want to know when it's equal to 0. Should factor this. And when you set all the pieces equal to 0, you'll find at a time of 1 and 3 minutes, the object is at rest. So think about the motion here, right? I'm imagining that time equals 0 would be the very start. So you're kind of being told here that from 0 to 1, the object is moving in a certain direction. And then at the time of 1, the object stops. Then from 1 to 3, the object is moving in a direction. It might still be moving the same direction, or it could have turned around and gone in the reverse direction. But then at a time of 3, the object stopped again. All right, it's resting. And then from 3 to infinity, it's going to keep going on. So when is the object moving forward? Well, moving forward, we know from yesterday, this would be when you have a positive velocity. You want to know when the velocity is greater than 0. And probably the best way to do this is to actually create one of those wiggle graphs. And we want to wiggle graph for velocity. Specifically, we want to know when the velocity is equal to 0. Now, it didn't say in the problem, but again, I'm going to assume that time starts at 0. So that's the smallest t value, my smallest x value I can use. I would want to put on here any time where my velocity was equal to 0. From the last problem, we knew that was at 1 and 3. And so then what you have to ask yourself is, what is the velocity equal to in any of these intervals? How about between 0 to 1? From 0 to 1, right, I can take a number like 1/2, and I would go up to my velocity formula, and I would plug in x equals 1/2. Now, or t equals 1/2. You only need to know if it's positive or negative. Right? I give you a minute to do the plug in x equals 1/2. Make sure you multiply and divide correctly. Actually, multiply and then add or subtract correctly. And I got a positive number back. If I plug in 1/2, all right, if I plug in the t, 3t squared, 1/2 squared is 1/4 times 3 gives me 3/4. And then when I've got negative 12 times 1/2, which gives me a -6, and then a +9. Remember, I don't need to know exactly what the answer is. I just need to know if it's positive or negative. 9 minus 6 gives me 3, and 3 plus 3/4 is 3 3/4. I have a positive velocity. So that tells me when I started at 0, when I went up to a time of 1 minute, I was moving in a positive direction. All right, my object was moving forward. Between 1 and 3, maybe 2 would be the best number to pick. Again, you can plug it into the velocity function. It should give you a negative back, which means from the time of 1 to 3, you're going backwards. And then finally, take a number greater than 3, plug that into your velocity formula. And you should get a positive back. Right? So the object starts at a time of 0, moves in a positive direction to a time of 1, then it stops. Then from 1 to 3, it moves in a negative direction. It's moving backwards. Then it stops. then a time from 3 up till whatever time you might be told to stop at, you're going to keep moving in a positive direction. So when was the object moving forward? It's moving forward from the intervals from 0 to 1 and from 3 to infinity. You can also write this as x, or 0 is less than t, which is less than 1, and t is greater than 3. Now there's a lot of other questions that we can figure out also. We can find out total distance traveled, all right, by finding the position at these different times. You can get some negative values that we include as positive values, right? Again, in the calculus class, these are some of the other questions that you'll be answering. Okay, second problem. Why don't you go ahead and pause this, copy this down, and then answer A for me. All right, here's my velocity and acceleration formulas. All right, so this rock was being thrown up in the air. It followed that path. I now want to know how long will it take the rock to reach the highest point. If you think about the path that would follow, it would look something like that, and we're looking for that. All right, it's an upside down parabola. You're looking for the vertex. You do have a formula you can use, or you can use calculus here. I'm going to use the calculus. So the flight of my path is going upwards at a positive velocity, and then my velocity, my derivative at some point, is going to hit 0. And then the rock's going to start coming down at a negative velocity. So I need to know, when is my velocity formula equal to 0? Oops, 32. Let's do this the right way. Erase equals 32t. T is equal to 5 seconds. It takes 5 seconds to reach the highest point. How high is that? Well, my position function would tell me that. S of 5, I'm going to plug 5 in my position function, and that's going to give me 400 feet as my maximum height. Now, what time does the rock hit the ground? Again, here's my path. I want to know here when it hits the ground. Now, don't assume that if it took 5 seconds to get to the highest point, it's 10 seconds to get the lowest. That's true if the rock actually started at a height of 0. All right, you would have that symmetry. But there's not always a guarantee of that in any of these problems. All right, the rock is going to hit the ground anytime my position S of t is equal to 0. So the object stops when the velocity is equal to 0. The object is on the ground when the position is at 0. 160t minus 16t squared equals 0. (16t times 10 minus t equals 0). Set each piece equal to 0. I get t equals 0 and t equals 10. All right, and this was in seconds. So as it turns out, it was at 10 when it hits the ground, and the reason for that is we actually started at a height of 0. So in the first 5 seconds, the rocket was increasing. In the last 5 seconds, it was decreasing, and then finally it hit that ground again. Now, the 10 is not the answer, or I'm sorry, the 0 is not the answer. The 10 is the answer. So the rock comes back and hits the ground after the 10 seconds. At what velocity and acceleration does it hit the ground? Well, if it hits the ground, if it hits the ground when t is equal to 10, then we're going to take 10 and plug that in. Come on. All right, just hold on tight. We'll come back here. All right, so when t equals 10, it hits the ground. So the velocity at 10, if you plug a 10 up there, you end up getting a negative 160. And that is feet per second. Okay, and that should make sense. It's negative because it was coming down at that speed. And my acceleration at 10, well, gravity's acting on it. The time really doesn't matter. Gravity is always going to be pulling at negative 32 feet per second squared, right? Until it hits the ground, and then you have a domain that is ended, and your acceleration and velocity and position are all going to be 0 after that. Okay, that's using position, velocity, acceleration. Right, at least here in the pre-calculus class. Now, in the calculus class, as I mentioned, you'd be using this a lot more, solving a lot of little more diverse problems that we have, right? Not hard to do, right? It gets a lot harder when we don't have polynomials that we're working with. So you will get into trigonometry as being part of these. You'll get into having exponents or logs as part of these, trig functions being part of these. You're going to have a lot of different types of functions to work with at that point. But you're going to know a lot more shortcuts, and it'll still be, well, it'll be almost as quick to find your velocity and acceleration formulas. Okay, with that, that's actually the last new thing that you need to know for this class. So I congratulate everybody for getting through this. I do have a worksheet tonight that you will have to take a look at online, all right, and either download or copy down the problems like the other ones. And then I do have a review over the unit for us to do. Okay, I'll talk to you again very shortly.